Hi, and welcome to this video, which is going to take you through everything that you really need to prioritize when you're revising for your Cambridge IGCSE sciences, chemistry in particular. And what we're going to go through is as quickly as we can the topic of states of matter. It's a very fundamental topic, actually. Um, and many students are actually really comfortable with it. Sometimes I find that they get a little bit too comfortable. So what I want to do is I just want to take you through a couple of areas where people tend to skip over or people tend to not emphasize. And these are really the areas that Cambridge Examination Board really want people to show their work, so to speak. The first thing that we can think about is how everything is made of particles. This is called particle theory. And particles on the move, that kind of leads on to the topic of diffusion. So you can think about that. Particles on the move, when you talk about liquid particles sliding over one another, when you talk about gas particles going going freely and colliding with each other, you can actually think about particles on the move. It's very different to solid particles that vibrate, and sometimes there's a little bit of a flaw in students' understanding. So what they might first of all try and get you to do is they might try and get you to say inadvertently that particles in a liquid or a gas vibrate, and they don't. They don't vibrate. They are free to move, and some of the phenomena that helps us understand things like diffusion is all to do with this random motion, of particles. You can imagine that you're at the start over here with a particle, and then it's moving along, and then suddenly, boom, it collides into another particle, and it changes direction. We just don't know which direction that's changing towards, and then boosh, it hits another particle, and then it just keeps on colliding and just moving in a random motion. Those would probably actually be like a gas. We can imagine if there's like there's no material, no particles in between these collisions. It's very easy for us to imagine, just like balls on a snooker table, that they just change direction. But what some students don't really realize as well is that this can happen more frequently in a liquid. And in a liquid, when you imagine a liquid, you can imagine that the particles are they're not in a random arrangement. And the thing about liquid particles is that they are still touching, but there's less of the area surrounding each of the liquid particles that's actually touching another particle. So what could actually happen here? Well, if we just focus on this particle over here and just illustrate that. So what could happen is that liquid particle could bump into there and then suddenly change direction and then slide over another one and then change direction again, just maybe change direction there. So it can actually happen within liquids as well. So you just have to keep that in mind. So particles on the move. And this is a nice question also that leads into the difference between the speeds of diffusion between liquids and between gases. And obviously gases, there's a lot of free empty space between the collisions that you have inside a gas, whereby with a liquid, they're all touching another particle, and it's very difficult for the particles that are moving randomly within a liquid to spread. So that's why diffusion takes place at a much slower pace. So I'd really think long and hard about the random motion aspect of particles on the move. The evidence in the lab that is a very popular way of testing it. So you can imagine that you have these crystals of potassium manganate. You can see an excellent representation of solids over here. They're in a random. They're in a they're in a regular arrangement, and you've got them stacked one on top of the other. But what you've also got to consider is that the liquid particles that is in this picture, you've got water crashing into and bombarding the particles in the crystal, and basically what happens is the attractive forces of the particles within the crystal are overcome, and brand new attractive forces towards the particles in the liquid actually form as well. So that is the reason why the particles from the crystal actually mix amongst the water particles in this demonstration. And then slowly but surely, what actually happens is the small particles from the crystals, they get caught up in the diffusion, in the motion of the liquid particles, and you have this concentration gradient, and the particles are seen to be moving from a region of high concentration to a region of low concentration until the uh, the overall concentration is the same throughout the solution. So everything just goes the same shade of purple in this actual example, and that's where that example then ends. So really make sure that you're prepared to talk about crystals and how they dissolve. I've seen examples where they talk about sugar at the bottom of a cup of hot tea, and how eventually, slowly but surely, the sweetness of the sugar is actually detected at the top. So that's a nice little test there. Moving on to bromine. So bromine is another one. So basically what happens is you start off with bromine, which is a volatile liquid, so it turns into a gas very, very quickly, and that is actually what's happening on the right-hand side. What candidates tend to do is they tend to forget that there are also air particles in the gas jars, as well as bromine particles that have now just evaporated. So what we actually have is a situation where at the start you have two gas jars, and there's a seal. So the gases can't mix, and you have air at the top, and then you'll have the bromine at the bottom. And a popular question that they can ask you is, well, what happens next and why? So what actually happens next is that you get an even distribution of bromine particles and air particles throughout both of the gas jars. It's not because the bromine wants to rise. If that was and completely rise because it's lighter than the air. If that was the case, then what you would actually have is you would have a situation where the bromine completely goes all the way to the top, and then the bottom gas jar is actually empty, and that's not actually what happens. So make sure that you look out for that one too. So the next aspect that I'd like to focus on is uh, changes, and this is actually something again that students are very, very comfortable with, but changes of state is the first difficult aspect that students get stuck on. So the easiest way to think about it is, like, say for example they give you a question where you're at room temperature. Room temperature, let's take it as temperature. It has a bit in it, so there you go. Let's try again. Room temperature. Temperature. Let's take room temperature as being 25 degrees Celsius. Okay, so 25 degrees Celsius. And look at these substances. Now, we actually know quite a few of these. We certainly, at this stage, you know that oxygen is a gas. And the reason why oxygen is a gas, because look at the melting point, and clearly the room temperature of 25 degrees centigrade is higher than the melting point of oxygen, so it won't be a solid, it will have melted. And look at the boiling point as well of oxygen, minus 183. So minus 183 is much, much lower than 25 degrees centigrade. So you can imagine that if you put oxygen as a solid in a room which is at 25 degrees centigrade, it would have melted. It then would have boiled, and it is now a gas. Let's assume that the temperature of the room can be sustained at 25 degrees as well. So that's the way to really think about it. And let's just go through these other substances as well. It's actually quite useful for us to consider. So ethanol will have melted, but ethanol's boiling point is actually at 78 degrees. So you haven't actually reached the boiling point. So ethanol would actually be a liquid. Sodium, well, the melting point of sodium is 98. So at 25 degrees Celsius, you haven't reached the melting point. So that remains as a solid at room temperature. Same with sulfur. Sulfur is a solid because it melts at 119. Same with iron, and same with diamond. Diamond is something that I'm sure that you're able to relate to very, very well. This next aspect is something that students get very, very confused about, and it's about changes of state on a graph. Now, the good news is that you don't really need to understand too much about the concepts behind it. You can get away with with knowing very little other than recognizing what to do when you get presented a curve like this. But I'll explain it anyway. This is actually a heating curve. The opposite of the heating curve that you're likely to see is a cooling curve. A cooling curve will start off as a gas, and then it will level off. Let's assume that it's a pure substance, so it's completely horizontal. Then it will be a liquid, and then it will level off as a complete flat horizontal line, and then it will go into a solid. So it could actually be the reverse of this. But let's just talk about a heating curve at the moment. Ice is a very popular substance to start. So you can actually think of ice being well below the melting point of ice, pure water, which would be 0 degrees centigrade. So what you actually notice is that once the melting starts, the temperature actually stays at 0 degrees centigrade until all of the ice is melted. And at GCSE, you don't need to go into it too much. But what you can do is, if you're really, really stuck on that, imagine that you actually have ice that's surrounded by water. Now, if and the ice is at 0 degrees centigrade. And let's say that some of the ice has actually melted to form form water. So if I can just draw that. So here is a beaker, and we've got some ice in it. And let's say, for example, for all intents and purposes, that it is again at room temperature. So you've got 25 degrees centigrade. And at this stage, the room's not cooling down, you get some water forming around the ice cubes. Now, why is it that the temperature doesn't rise as soon as the melting starts? Well, you can imagine that if you had the water is obviously going to have a temperature that's above 0 degrees centigrade. You might think that, but if it did have that, you would then think, right, okay, so the water particles have kinetic energy, so they've got more kinetic energy. They're moving, they're sliding over each other. You can imagine that that is then situated next to an ice cube, and the transfer of energy will actually go from the water to the ice cube. And that is actually what keeps everything level at 0 degrees centigrade. So the ice will melt, but the temperature of the ice water mixture will stay at 0 degrees until all of the ice is melted. Physics, you actually call that latent heat of fusion. There you go. Okay, so that's the principle behind it. If you really, really wanted to know, the good news, like I said, is that you don't have to justify. You just have to be able to recognize what is happening in the change of state on the graph. So the horizontal line represents the melting of this ice, and it's fixed at 0 degrees centigrade until all of the ice melts. And then after that, if you are continuing to warm it, so say, for example, in this experiment, you could actually be having a beaker on top of a tripod, and you start off with ice cubes, and you've got a thermometer, and you're measuring temperature. So the temperature right at the very beginning will be below 0. You've just got it out of the freezer, and let's say, for example, you are just heating it with a heat source. Okay, so what then happens is you get to 0 degrees centigrade. You melt all of the ice. It turns into water, and then what happens is the water starts to warm up. Now it's pure water as well, so you then reach 100 degrees centigrade, and then what happens is at 100 degrees centigrade, 100 Celsius, you will get every single particle inside that water having sufficient energy to escape to a gas. So you then have what's called boiling. You might actually get some gas particles forming before you get to 100 degrees centigrade because you're heating it constantly, and as you're heating it, some particles may have enough energy to escape at the surface, and that's the distinction between evaporation and boiling. But once you have boiling taking place, the water mixture stays at 100 until everything gets vaporized, and then once you have all of the water particles as a gas, you could, in theory, just be heating a gas. So the gas particles of steam will then bump off the inside. It's all nice and hot, and then as a result of that, you're actually heating the water, the gaseous water, the steam, to a temperature that is actually above 100 degrees centigrade. So that basically then justifies what's actually happening at that part. So all of that is nicely represented as a heating curve. And if you go in the reverse direction, if you go from a gas to a liquid to a solid, that is actually what you would expect to see. Okay, so that talks to you about what happens when you heat pure substances. Just make sure that you understand that when it goes flat, when you have the line going horizontally, that means for a pure substance you've hit a point where it's changing state. Okay, and you'll get pure substances going flat because pure substances have no other impurities. If they did have an impurity, then a pure substance would actually have a rise in boiling point and a deflation of melting point. So that's what happens. It's a nice way of testing to see if you've actually got a pure substance, because pure substances have sharp and clear melting and boiling points. Okay, so if we move on to particles in solid, liquids, and gases, I'm just going to overemphasize what is actually happening inside the liquid. So you must make sure that you understand that the liquid particles are almost as close as the solid particles on average. Okay, but that also means to say that this picture takes into account the fact that there is an irregular arrangement of the particles inside a liquid, and the particles in a liquid will, on average, touch less particles surrounding it. Please don't consider that as being a model. I'm just going to tick this one. Don't consider that as being a model where you have liquid particles like this, where we have significant gaps between the particles, and the particles not being in touch with each other as at all, really. Okay, this is a very, very wrong model. Okay, so I just put the extra particles in there. So they are still close together. They aren't in a lattice, and the forces that are holding them together are less effective than the forces in a solid, if they were in a solid, because they have more kinetic energy stored within the particles themselves. They actually are able to overcome the forces that are in between. That's the correct level of understanding. So really, what you need to consider, I'm just drawing at the bottom of the screen and fixing this up. This is a better picture of what's actually happening when you have a melting liquid. So no gaps in between them, and got a couple of extra ones that are maybe on top. And to be fair, I think looking at the resource that we are looking at right now, maybe this might actually be representing the top layer, but we've also got to make sure that that we put across the right picture. Okay, so these are this is so this picture over here. There's something very, very wrong with this picture. Okay, and this picture is also a little bit of a trap because this should be random. This picture over here, some people may consider this to be a valid picture of liquids in their minds. And again, what we need to do is we need to realize that we have more particles in them and they are sliding over each other. I can't overemphasize that. That's how it should be. And we have to try and consider the fact also that this picture over here has the same number of particles as the picture in the middle. Okay, so I suppose this is a visual representation of what I'm hoping is happening in your mind if you are mistakenly thinking that that there are gaps in between the liquid particles. Same number of particles, and then what you actually have is you have a certain number which are actually trying to escape, and if it's boiling, then actually all of them want to escape at the same time. That can only happen at the boiling point. But if you actually have evaporation, which can take place when you have a liquid, I should also emphasize that the liquid particles do not get bigger in particle pictures. So if you have evaporation, maybe you might have one or two escaping. Maybe that one just bumped into something over here, like an air particle, and it changed direction. But there we go. And that's basically what happens with evaporation. So the more kinetic energy that's stored within the liquid, the more particles that actually have enough kinetic energy stored within them to escape. Make sure that you actually have the right names for the changes. So solids going to liquids as melting, liquids going to gases. They could be evaporating, they could be boiling. Gases going to liquids are condensing. Sometimes you can call it liquefying. Condensing is more common as a word. And then liquids going to solids. You could say it's solidification, but freezing is the word that's more popular. You can also get sublimation, where you have no transition through a liquid, and a solid can actually turn into a gas. Now that can occur with substances like carbon dioxide. It can also occur with substances like iodine. And the opposite of sublimation, sometimes it's called sublimation as well, but the opposite is deposition. It's another word for it, so I'm just going to put that one there. Okay. This is another closer look at gases. I think what you need to just remember is that when you are doing questions like this, the pressure of gases, make sure that they are in a random order. Okay, the pressure of gases comes about when you actually have gas particles hitting the sides of containers. Okay, so that's where gas pressure really comes from. The rate of diffusion of gases is actually a very popular question. So it's an experiment that involves ammonia solution in one end of a long glass tube and hydrochloric acid concentrated hydrochloric acid at the other end. What basically happens is you get evaporation of the gases. So the liquid particles gain enough energy and they evaporate and they start to diffuse. They travel through and they bombard and are bombarding the air molecules that are inside. So that actually happens with both of the gases. However, what we actually notice is that the hydrochloric acid, which is forming hydrogen chloride gas, that actually stays towards the end that you added it to. The ammonia solution, which makes ammonia gas, actually seems to fly through further and faster through the tube. Now, the reason being is that the ammonia gas particles are actually lighter than the hydrogen chloride particles. So when you get a hydrogen chloride particle bombarded, it's a representation of the hydrogen chloride particle. So when you get a hydrogen chloride particle bombarded, what actually happens is its mass is very, very large. So when a particle of air collides with it, it doesn't seem to move. It doesn't seem to move very far because it's got inertia. It's when you try and move large objects, it's much harder. You have to actually add you have to actually push it with a greater force. So they don't actually shift too quickly when they're bombarded by air particles. Whereas with an ammonia particle, just represent that here. If an ammonia particle hits an air particle, there's your air particle. Represent the nitrogen. And there's your hydrogens. The ammonia particle is actually lighter. So if you're at the point where you are starting to revise for your real exams, and you've covered everything, then you will appreciate that the relative molecular mass of ammonia is 17, and the relative molecular mass of hydrogen chloride is 36.5. So it's so ammonia is approximately half the mass. So when you actually have that collision taking place, the ammonia particle just shoots off completely, whereas the hydrogen chloride particle could actually just shoot off in a much slower pace. And that basically justifies why you get a white smoke forming closer towards the hydrogen chloride end. The white smoke, by the way, is a compound called ammonium chloride, and the ammonium chloride forms from ammonia. So we'll put the 3 below, plus HCl. So it actually forms NH4, which is ammonium, Cl. That's the white smoke, and it's a solid. This is another part. It's another substance that actually undergoes sublimation and deposition. So basically, what happens is you form a solid, and you bypass the liquid phase of ammonium chloride. And what would actually happen if you actually raise the temperature? It's a very good question. Well, if you raise the temperature, the ammonia gas particles would actually move faster. The hydrogen chloride particles would move faster as well. So the white smoke would actually form in a shorter time. I'll leave it for you to think about whether the white smoke actually forms more towards the ammonia end or the hydrogen chloride end. It's actually a nice exercise for you to think about. Now that's basically everything that you need to know about states of matter. So just a quick summary, because some of you are preparing for extended and other people are preparing for core. So in extended, make sure that you really get your head around the diffusion tube experiment. Make sure that you're thinking about that. How and why the temperature affects the rate at which the gas diffuses. That's all to do with the fact that there's more kinetic energy stored. Therefore, they move faster. on average, compared to when they're at lower temperatures. And for the core, 2 examples of evidence from the lab that matter is made of particles. Well, the 2 examples that we thought about were potassium manganate and water, and the other one was bromine and air, that diffusion through the gas jars. Diffusion, movement of particles from an area of high concentration, a region of high concentration to a region of low concentration, until down a concentration gradient until the concentration within the container is even. How does it happen? The answer is random motion. Okay, random motion. Okay, 3 states of matter, solid, liquid, gas, give their physical properties. So solids are hard, they have a fixed shape, they don't take up the shape of the entire container. Liquids, they can flow, unlike solids. They can take up the bottom of their container, but they don't take up the entire container. Gases, they can take up the entire container, they can flow as well. And describe and sketch the particle diagrams in each state. Solid seems to be something that people are successful with. Liquids is the one that people have a problem with. So again, it's an irregular arrangement with just about all of the surfaces of each of the particles touching another particle. And remember that liquid particles slide over each other as well. So you could represent the motion like that. Describe how substance changes state when you heat it, and explain this using the idea of particles. Well, that is the so substance changes state when you heat it, and that's the particles gain energy from their surroundings when they are heated. The amount of kinetic energy stored in the particles increases, and that is then until the forces in the previous state are overcome. So if it starts off as a solid, then what you need to do is you need to say, right, okay, well, solids, they're vibrating, and then when you heat them, the forces between the particles are overcome, and then you have like a liquid, which I've already drawn. So this is a solid, that's a liquid, and then eventually, if you're providing energy from a source, the liquid particles will have enough energy to escape, and escape they do, and they escape, and then they travel freely. Explain and use these terms: melting, boiling, evaporate, condense. Melting point, that's that's the temperature at which a solid turns to a liquid, which is also the temperature that a liquid, when it's cooling down, will turn back into a solid. Boiling point, same kind of principle, when a liquid going to a gas. So the temperature that takes place, gas going to a liquid, that will actually also take place at the boiling point. The freezing point is another synonym for melting point as well. Sketch and label a heating curve. So you start from solid, goes like that, liquid. So I'll talk you through this. So with a heating curve, so start off with a solid, then melt the solid, then the liquid, melt the liquid, boil the liquid. That was really bad. Boil the liquid, and then it turns into a gas, and then you warm the gas. Explain why gas exerts pressure is because the particles are bombarding the walls of the inside of the container. So pressure equals force over area. So there's a force given over an area, and that's and the combination of all of the gas particles hitting the inside of a container gives you pressure. Why pressure increases when you heat a gas? Because the gas particles move quicker. And why does it increase when you compress the gas into a smaller space? It's because you're decreasing the distance that the gas has to travel before it hits the wall. So that's the reason why the pressure changes. Okay, so that's pretty much it. And on the on the video now, you can actually see that there are some examples of questions that you could be typically asked, and I'll leave it there. Thank you very much for watching. If you like the video, then please just leave a comment. It's just a really quick summary of everything that you need to know for state of matter. And good luck with your revision. I really hope that you do very, very well in your GCSEs. Take care, everyone. Bye-bye.